Hello everyone, in this presentation I'll be analyzing the motion of projectile using both experimental data and computational models. This lab explores how physics principles, particularly Newton's second law and air resistance, influence projectile motion. Projectile motion occurs when an object moves through the air under the influence of gravity. It is a form of motion experienced by an object's particle that is projected in a gravitational field, such as from Earth's surface, and moves along a curved path under the action of gravity only. The purpose or goal of this lab was to record and analyze the motion of a thrown object, compare it to its computational model, and examine the effects of air resistance. The formulas needed for this experiment are that the motion of the object follows Newton's second law, F equals ma. The force due to gravity, F equals mg, acts downward. Air resistance, modeled as FD equals bv squared, opposes motion and depends on velocity squared. And the assumptions are that no other forces are applied to the object. For this experiment, I threw a scrumble up paper ball and recorded its motion. The mass of the object was 0.1 grams and the initial height was just 0 meters. The video was taken with a stationary camera and the ruler was used for scale. I used the tracker software to analyze the object's motion. The x-axis was placed along the floor and the origin was set directly below the starting position. The tracker provided the object's trajectory, velocity, and acceleration data, and here you can see those results graphed. I then created a computational model that only included gravity. The code updated the object's position based on acceleration due to gravity. The resulting trajectory followed the expected parabolic path, and here you can also see the graph of those results. Then I modified that model to include air resistance. The drag force acts opposite to the velocity and is proportional to v squared. This caused the object to travel a shorter distance compared to the gravity-only model. Here I compare the experimental data with both computational models. The gravity-only model overestimated the range, while the model with the air resistance closely matched real-world data. This confirms that drag plays a significant role in projectile motion. Possible errors include measurement inaccuracies in the tracker, the frame rate of the video affecting data precision, and the assumption that drag is proportional to v squared, which may not be perfect for this object, which was a scrumbled paper ball. In summary, this lab demonstrates how computational models can predict projectile motion. The gravity-only model overestimated range, while the gravity plus drag model aligned more closely with the experimental data, confirming the significant role of air resistance. So here are some what-if scenarios. What if the object was thrown in a vacuum? If this experiment were conducted in a vacuum, the object would follow the gravity-only model exactly, since there was no opposing drag force. What if the object had a different shape? The crumbled paper ball experiences different drag than a smooth sphere. A streamlined shape would experience less air resistance, increasing range. What if we change the launch angle? The optimal angle for maximum range in a vacuum is 45 degrees, but in real conditions with air resistance, the ideal angle is slightly lower. That's the end of my presentation. Thank you so much.